nanohub.org.
Good morning, everybody, and you have been hearing from Professor Reifenberger about force distance curves and what is the fundamental physics behind interactions, force interactions between a few tens or hundreds of atoms on a tip, and between those and the substrate atoms and so on. So today we're going to make a switch and move towards what happens when you take those interaction forces and then bring a cantilever, an AFM tip, close to the surface and move away from it. And a lot of interesting things happen, and understanding it is essential to interpreting what is called FZ curves in atomic force microscopy. Okay? So let's begin with what we call the FD curve. Okay? F stands for the tip sample interaction force. D stands for the gap between the tip and the sample. And over the last week, you have seen examples of force distance curves between tip and the sample that can occur or can change depending on the type of interaction there exists. Okay, so let's review some of the basic concepts that Professor Reifenberger has been going through. But effectively, the interactions you measure in atomic force microscopy are not between individual atoms, but rather between aggregates of 10 to 100 atoms on the tip and 10 to 100 atoms on the substrate. And effectively, what is going on, if you can imagine, is there are going to be atom-atom interactions between the blue atoms on the tip and the green atoms on the substrate. But what we do is we sort of integrate these atom-atom interactions over the volumes of the interacting material. And once you do those integrals, as you've seen, you get an effective force, and that force is effective between the volumes of the tip material and the sample material that are interacting with each other. And we get an effective force, F, TS, force, tip sample force, as a function of D, which happens to be the smallest gap between this cluster of atoms on the tips that's interacting with the sample. Right, and so some of the examples that you've studied in the past few days include the DMT contact mechanics model, which, as shown in this graph on the top right, plots the tip sample interaction force as a function of D, the gap between the tip and the sample. And of course, there's a lot of interesting physics in these FD curves. So for example, if you look at the attractive regime where the forces are negative, you actually find a van der Waals-like behavior where you get a inverse square law of interaction forces. And so if you sort of know this part of the curve, you're actually looking at Hamacher constants, fundamental van der Waals forces between the tip and the sample. And once you reach a point where you say some sort of contact is initiated, the interaction force goes up, becomes positive, you get repulsive net interactions between the cluster of atoms on the tip and the cluster of atoms on the sample. And this part of the curve is telling you information about the elasticity of the sample, about repulsive interactions between the tip and the sample. So there's a lot of really deep physics involved, from Hamacher constants to even adhesion, to elasticity of the sample, inelasticity of the sample. So a lot of interesting surface physics is probed or is contained within these FD curves. Okay, you've also seen, I just want to point out to you an example where the FD curve itself turns out to be hysteretic. What it means is that you just take this cluster of atoms and the cluster of atoms on the tip, on the surface, you bring them close together and you move them apart. The interaction forces are not the same when you move in versus going out, and you get hysteresis like is shown here. So for instance, what you see in the bottom right is an example of what's called a JKR interaction model, where as the tip is brought in, there's a sudden negative force that comes in due to the atoms on the tip actually necking, leaving their positions and forming a neck with the sample. And so when you pull away, you're literally breaking these bonds as you pull away. So that when you pull away, you follow the green line, and there's a hysteresis. So this hysteresis pretty much happens because of, necking effects, if you will, and pulling away from it. But necking not due to the presence of water layers and so on, but the material itself being soft, the atoms move and literally make a bridge and pull away from it, okay? So FTS, F versus D, can either be single valued, as you see in the DMT model here, and we call those FD curves as conservative interaction forces because the forces only depend on the gap between the tip and the sample D. On the other hand, models like JKR are considered dissipative tip-sample interaction models, or dissipative FD curves, because as you move in or move away from it, you actually have a net loss in energy, which, as was discussed in the last class, is really the work of adhesion in separating the tip from the sample. So this is great. F versus D contains in it all this important physics. However, the unfortunate thing is that in atomic force microscopy, we do not measure this directly. So this is where all the physics is. This is where we want to be and understand forces, understand the physics on the surface, but this is not what we measure in atomic force microscopy. And this is one of the big challenges. So the question is, what is it that you would measure in atomic force microscopy? Well, in the AFM, you do not measure F versus D, but rather you measure F versus Z. And this figure illustrates it very nicely. But basically, the cluster of atoms on the tip, whose interactions you want to probe with the surface, is actually a part of a bigger conical tip, right? And that conical tip, or big tip, is connected to a very large cantilever, could be 200 microns long. And what you move, or what you try to control in an atomic force microscope, is not the D, the gap between the tip and the sample, but rather Z, which is the motion of the base of the cantilever up and down. So ideally, what you would like to do is to have, if your goal is to get F versus D, which is where all the physics is, you want to be able to step the tip through, evenly in small increments in D and study what the forces are. Unfortunately, you can't do that in atomic force microscopy. What you can do is step through equal increments of Z, which is really the Z piezo actuator in an atomic force microscope that moves the cantilever up and close to the sample. Not surprisingly, there is a difference simply by looking at this figure between Z and D, correct? And so what you measure is F versus Z, but the physics is in F versus D, so there's a very important conversion process that needs to happen. So what you do in atomic force microscope is you move Z, which is the Z piezo displacement, which moves the base of the cantilever up and down. Using the photodiode, what you do is you actually measure delta, which is shown here as the deflection of the cantilever. And if you know the spring constant or the bending stiffness of the cantilever, you can convert the bending, the deflection of the cantilever, delta, to the interaction force between the cluster of atom on the tips and the volume on the sample that's being probed. And so you're basically measuring FTS versus Z in an AFM experiment when you move the cantilever close and far away from the substrate. And simply by looking at the geometry of this, you would say, gee, that's all right, but it's probably not such a difficult thing to convert FZ to FD, because just by looking at the geometry, you would say that, well, for every force value, I see there's a trigonometric relationship, there's a geometric relationship that suggests that Z plus delta is going to be equal to D, the tip sample gap. So when delta is negative, it's bending down. Delta is positive, it goes up. So D should be equal to Z plus delta. So if at every force, if we know what the cantilever deflection is, we only need to add it to the Z position to get the value of D, which is great, and that is correct. However, of course, You also need to include the height of the tip in this geometric calculation. But remember, as Professor Reifenberger has told many times last time, the notion of where d is actually set to 0 is not very clear. It's somewhat arbitrary. So we don't need to worry about the height of the tip itself for the moment. We'll just choose another criterion to decide when d equals 0. But the key thing is, if you measure F versus Z, for every force value, you could, in principle, take the Z value, add the measured cantilever deflection, and get d from it. And this is what is usually done. But this process is not very easy either. You'll see it's not that straightforward. There are a lot of interesting things happen when you take a flexible cantilever and bring it close and far away from the sample. There are cantilever instabilities. There are ranges of the FD curve that you're unable to access. Really cool stuff that happens when you bring a cantilever in and close to and far away from the sample. So we're going to now move a little and then try to understand how does the cantilever bend due to these interaction forces. The cantilever itself is like a beam, of course, with a sharp tip at the end of it. And the basic principle that we're going to be looking at is you have a cantilever beam, you apply a point force F at the end of it. What we're interested in looking at is how much does it deflect up, delta, and how much does it bend, what is the bending angle, theta, at the end of the cantilever. The reason is, as you have seen in the last classes, when you use a photodiode detector, what you measure is really the rotation angle at the end of the cantilever beam. So what we're really interested in doing is how do you convert the force applied from the tip sample interaction to a bending angle or a slope at the end of the cantilever. Now, we're going to study this in some detail in the next few slides, but the key result is going to be that if you have a force at the end of a cantilever beam, the deflection delta at the end of it equals the applied force times the length of the cantilever squared divided by 3 times EI, E being the Young's modulus of the material of the cantilever, I being a quantity that's called the area moment, which is given by the width times the thickness cubed divided by 12, where B, H, and L are defined in the figure on the top left. Right? You also find that theta, the bending angle, is also linearly proportional to the force at the tip. And this number K, which is 3EI over L cubed, is called the bending stiffness of the cantilever. I will refer to it as K or K cant, depending on the slide at question. So what we're going to do now is to prove from basic mechanics these two relationships. Okay, so we're going to go into the guts of basic cantilever mechanics and understand how a cantilever bends, and then we're going to couple it to the interaction forces to figure out what happens in an FZ curve. Okay, so let's go to a classical beam theory. This is going to be a recap of undergraduate mechanics and materials, but basically we're talking of long slender objects that are subject to many external loads shown by the red arrows. And one of the key things that you have to take into account when you do beam mechanics is these things called internal resultants. And let me explain internal resultants first. But basically, if I were to take a section of this beam at the dashed line as shown, and then look at the part to the right of the section and draw a free body diagram of it, that's what is shown here. Now, it's very clear that under the application of the applied load, the entire beam is in equilibrium. It bends and it's in equilibrium. And so every piece of it should also be in equilibrium. So even this piece that's to the right of the section should be in equilibrium. The only way you can balance the applied forces shown in red is if the part of the beam to the left of the section applies some forces and moments to this part of the beam to the right of the section in order to keep all this in equilibrium. Right? And so those forces are going to be an axial force F, a bending moment M, and a shear force V. These are the moments and forces required, or applied, if you will, by the part on the left of the beam to the part on the right in order to keep the part on the right in equilibrium. Because if these forces are not applied, this part on the right is going to fly away F equal to ma, right? It's going to accelerate and fly away. But the beam as whole and it's under equilibrium, so it can't happen. All right, so these three quantities are called the internal resultants. V is called the internal shear force, F is called the internal axial force, M is called the internal bending moment, and they vary as a function of x along the length of the beam. All right. Now, there are some important relations you can derive that connect the internal shear force, internal bending moment, to the applied load P of x on the beam. All right. These are the following, and how you do them is as follows. Let's say you have a distributed load as shown here, an applied load P of x. This is a force per unit length applied along the length of the beam. We make a section of the beam at a location x and then cut off a sliver that's delta x thick. That's what is shown on the top right? So you've gone a distance x and then you've gone delta x more and just cut off the sliver. And so on the left-hand face, you've got the internal shear forces V of x, M of x, and we're ignoring for now the axial force because after all, we're looking at, deflection of beams due to transverse forces. We're not pulling on the beam, so we're not going to worry about internal axial forces. But on the left face of the section, you're going to get M of x, V of x. On the right-hand face, the values of these internal resultants have changed to x, M of x plus delta x, V of x plus delta x. If you do a force balance of this element along the y direction, and take the limit as delta x goes to 0, you get a very nice relationship that if you know the loading on the top of the beam, P of x, as a function of x, you know how the internal shear force varies as a function of x. So dV dx equals P of x, okay? In the same way, if you do a balance of moments in this free body diagram about the spot, the black circle shown on the right, if you do a balance of moments, take limits as delta x go to 0, you get a second important relationship, dm dx is equal to V of x, okay? So this is very basic mechanics of materials, but what it basically shows is that if you know the distribution on top of a beam of force applied on the beam, you can get the internal moment and the internal shear force as a function of x. All right. Now, what we need to do is to connect the shear force and bending moment to stresses and strains, because strains refer to deformation of the object, and what we're trying to get to is, given the load, what is the deformation of the object? So there are two steps to it. We go from the applied load to the internal shear force and moment, and then from the internal shear force and moment, we're going to go to the stresses. From the stresses, we're going to go to the strains. That's the theory behind this. So one of the key assumptions in classical beam theory is that if you take a beam that's initially straight and you sort of look at these cross sections that are perpendicular to what's called the neutral axis of the beam, the dashed line, when you bend it, the assumption is, as shown on the right, that the neutral axis bends, and the cross sections of the beam that are initially perpendicular to the neutral axis on the top, they rotate to continue to be perpendicular to the neutral axis, as shown on the right. This is the basic assumption behind what's called thin beam or Bernoulli-Euler beam theory. Using this assumption, you can actually figure out what is the axial strain in any element of the beam. For those of you who are not familiar with it, strain just refers to, if you took an infinitesimal line element that's embedded inside the material, as you deform it, what's the change in length divided by original length of that infinitesimal element, right? So if you chose, for example, an infinitesimal element down here on the right, that's located at a height y above the neutral axis, and you bend it, what you would see, and you bend it locally into a radius of curvature rho, what you can easily see is that the stretching or the compression of this little fiber relative to when it was not deformed is given as the following. It's epsilon xx, that's the change in length of that fiber due to bending. So how do we figure that out? The first term, rho minus y delta theta, you will recognize as the length of this fiber after the beam has been deformed into a radius of curvature of rho. That's the first term, minus the original length of the fiber when the beam was straight. That's the second term, rho delta theta, divided by the original length of this fiber. And you do that, you get the strain is going to be negative y divided by rho. It means that when you're at the center of the beam, y is equal to 0, there is no strain. And you move up, the strain increases. When you go down, the strain increases. So what it means is when you bend a beam, the strain is 0 at the neutral axis. It reaches a maximum on the top surface, minimum on the bottom. What it physically means is, let's say you bend a beam up, the fibers above the neutral axis are getting compressed, fibers below are getting stretched. That's what it means. And from basic Hooke's law, you know that the stress is going to be, at least in one-dimensional stress situations, stress is going to be elastic modulus times strain. E is the elastic modulus, and so you find, therefore, that sigma xx, the stress, is also given very simply. You can make a further assumption that the radius of curvature rho is simply related to the square of the derivative of the deflection with respect to x. So d squared w dx squared gives you effectively the curvature, right? So the key thing then is that sigma xx, which is the stress, varies across the cross-section. So we're going to now try connecting the stresses to the bending moments and the shear forces. How we do that is, we got a beam, width b, height h, and at a distance x, we look at a cross-section. What we have just learned is that if you apply, or if there is an internal bending moment m of x at that cross-section, you're going to have a stress distribution that varies through the cross-section. So if you apply the bending moment as shown, the top fibers are going to be in compression, so there's going to be a compressive stress shown by the arrows pointing inwards from the surface. At the bottom, they're going to stretch out and the arrows are coming out of the surface. And so what we now want to do is to correlate the stress distribution sigma xx to the bending moment m, and we do that by recognizing that if you take a little square patch of the cross-section as shown in the figure, and you multiply sigma xx by the area of that patch. Remember, stress has units of force per unit area. So if you multiply stress by an area, you get the force acting on that unit, on that area. So on the square patch, taking sigma xx multiplying by dy dz, which is the area of that square patch, gives you the force on the little square patch. You simply have to then integrate and that force causes a moment about the neutral axis. So that little square patch is located at a height y above the neutral axis. So you take the force acting on that patch multiplied by the height, it gives you the contribution to the moment from the stress on that little patch. And you integrate over the entire cross-section using the relationships derived in the previous slide. For a rectangular beam, you come up with a relationship shown here, which is the bending moment must equal a quantity EI times the second derivative of the deflection with respect to x squared. Or in other words, this term is simply the curvature. So EI times the curvature, where I is BH cubed over 12, is called the area moment of the cross-section, is the main relationship. And in the previous slide, we derived that, well, if you know the bending moment, you actually know what the shear force is, because dm dx was going to be equal to v of x. So just a single derivative of this, and you get vx equals ei, third derivative of the deflection with respect to x cubed, right? And if you remember, we also had a relationship that dv dx was going to be equal to p of x. So when you put that all together, you get this fourth order differential equation that tells you how to solve for the deflection of the neutral axis, w as a function of x, in terms of the load applied on the top of the surface, okay? And so you need to solve this differential equation with boundary conditions at x equal to 0, x equal to L, all right? So I can show you a couple of examples. This is example 1, and I can encourage you to work this out yourself. But let's go to example 2, which is more relevant to what we've been doing. You have a beam and you have a force applied at the end of it. Well, what happens in this case is, remember, there is no distributed force on the top of the beam. So P of x is going to be 0, right? So you have EI d squared w dx squared equal to 0. You integrate it once, and you get a constant of integration C1. You integrate it twice, you get another constant of integration C2, all right? You integrate it a third time, you get theta of x, which is the bending angle or the slope of the beam as a function of x, being 1/2 c1x squared plus c2x plus c3. And finally, you do one more derivative and you get the deflection curve as a function of x. It's a cubic function of x, okay? So that's what 4 derivatives gets you to. But we need to now evaluate C1, C2, C3, and C4, the constants of integration. And you have to use boundary conditions for that. So on the left of the beam, you have a situation where the deflection of the beam and the slope are constrained to be 0 because it's clamped at the left end. And on the right-hand side, since we are only applying a point force due to the force between the cluster of atoms on the tip and between the sample, really that applied force must be the shear force at the free end. So you have the boundary condition becomes the shear force EI d cubed W dx cubed at L must equal the force. And since we are not applying any moment at the free end, therefore the internal bending moment should also be equal to 0 at the free end. Okay? So these are the boundary conditions, and you take this form of Wx and plug it into these 4 boundary conditions, and you actually find that C3 and C4 would be 0, C1 and C2 are given as follows. And so C3 and C4 are actually 0, and so these are the constants of integration. So what you find is the shape of a beam when you apply a force at the end is actually described by a curve that is x squared plus something times x cubed. It's a polynomial which has a quadratic term and a cubic term. That's it, nothing more. There's no quintic term, nothing. It's just quadratic and cubic terms. That's it. And so by simply evaluating the expression for W of x at x equal to L, the free end of the beam, you're able to get expressions for the deflection at the end of the beam, 1/3 FL cubed over EI, and the theta, the bending angle at the end of it, is FL squared by 2 EI. Okay? Now, one important thing to note is that the ratio of the angle that you get at the end to the actual deflection delta at the end is 2/3 L. This is sometimes called the optical lever length, because remember, what you measure in an AFM with the photodiode is the angle theta, but you're inferring delta, the actual deflection, because the relationship between theta and delta is a geometric quantity connected to the length of the cantilever. Okay? So, again, this illustrates the point that when you have a 4-quadrant photodiode detector in AFM, as you bend the cantilever up and down, due to the tip sample forces, the reflected spot goes up and down, and it's a 4-quadrant photodiode. So if you want to get the up and down signal, you look at A plus B gives you the deflection up, C plus D gives you the deflection down, so you do A plus B minus C plus D, the up minus the down signal give you the vertical deflection. But interestingly, in an AFM, you can also monitor the twisting of the cantilever by simply looking at B plus D minus A plus C. In other words, right minus left signals coming out of the photodiode. Okay, so you can do both. So it measures angles, but the angles, depending on what you want to do, can be either bending angle or twisting angle. Both can be measured at the point where you shine the laser spot on the cantilever beam. Okay? All right. So now we have the basic relationships of bending of a cantilever under an applied force. Now let's zoom out a little bit and look at what an AFM does when you try to do FZ curves. Okay? So you have a sample here. This is a cantilever holder, and you're trying to measure the deflections of this cantilever beam using an optical path that goes to the photodetector. So this is a photodetector. You shine a laser beam. There's an optical path, usually with mirrors, that takes you to the photodiode. So as this cantilever bends, this path of the reflected beam changes. It goes up and down, giving you a bending signal out of it. However, you also change Z. Now you can change Z in 2 ways. What I showed you in the previous slides was you have some AFM systems where the base of the cantilever is moved up and down to change Z. In some other AFM system, the sample is moved up and down to change Z. Nothing really changes. The same idea remains that F versus Z is not the same as F versus D, okay? But this is the basic idea, all right? So you change Z by either moving the sample up with the piezo or moving the base of the cantilever down by a certain amount. You measure the force by measuring the deflection or the bending angle here, using the cantilever spring constant to figure out what the force is. So you get force versus Z. And you need to convert it to F versus D, okay? All right. Now, let's try to understand this a little bit, okay? One of the key things that happens when we take now this cantilever beam and bring it close to a sample is the following. Z, remember, is the gap between the base of the cantilever and the top of the sample. But when you bring Z close and come close to the sample, you have an interaction force FTS. As a consequence, the beam is going to deflect, right? And it goes to an equilibrium position which we call D star, okay? So really our question is going to be, you know, how does D star and delta, which is the deflection of the cantilever, change as Z is reduced, okay? So we're simply going to look at, you change Z, how does the gap change, and how does the delta, the deflection, change as you approach the sample and move away from it, okay? And we'll take this particular example. We have a FTS as a function of D, that's shown here. This looks like a Leonard-Jones-like potential, right? So you have negative forces, and then when you come closer, you get repulsive interactions, okay? So now, what we have shown is that you can model the entire cantilever as a spring with a certain spring constant, EI, 3EI over L cubed. So let's make life simple and replace the cantilever with a spring, okay? And the tip is represented as a sphere. So you got a sphere, and you replace the entire cantilever beam by a spring. All right? Now, when you move Z by a certain distance, you actually find that the cantilever deflects up a certain amount, delta, okay? And the gap D is going to be equal to Z plus delta, or in other words, the deflection is going to be D minus Z, okay? We discussed this before. Now, what we want to do is now, given this F versus D, we would like to predict what will F versus Z look like, okay? And in order to do that, we look at the free body diagram of the tip shown up on the right. What you have is a force from the bottom, FTSD, and what you have on the top is the restoring force from the cantilever. So the spring is getting compressed by an amount delta, which is D star minus Z. So what's going to happen is, when you change when you change Z, what's going to happen is the gap that the system settles to, D, is going to be decided by the equilibrium of these two forces, okay? And it's not straightforward because while the force on the top shown in green is linear with respect to D, the force at the bottom is a very complicated function of D. So at every Z, you have to balance these two forces to figure out, well, at what D do these two balance out? And we can study this graphically as follows. So you have on this curve F as a function of D, shown in red, and at a certain Z, you've got the base of the cantilever basically located, and graphically you get this equilibrium between these two forces whenever these two curves intersect, okay? So the red curve is F as a function of D, and the green curve is actually how the restoring force K changes as a function of D, right? So at a given Z, the restoring force as a function of D is simply a straight line. You change D, and it changes by a straight line. So if you want to figure out, at a particular Z, what is the D, the gap that you're going to be located at, you simply need to look at the intersection between these two graphs, okay? So it's simply a graphical representation of the free body diagram on the right. And since this is Z, and let's say the intersection occurs at this point, then the delta, deflection of the cantilever, is simply the difference between the Z location and where the intersection occurs, that is delta. So this is, by the way, described very well in the reader in the article by Capella, Capel, et al. Okay, so now we're going to step through this one by one. We're going to move Z closer. We're going to move the base of the cantilever closer to the sample. We move it close to the sample and look at the intersection point. So you move the Z close to the sample, the intersection point is as shown. Very quickly you realize that as you come closer to the sample, the intersection occurs at 3 different points. What this means is that there are 3 different values of D, the gap, at which these forces equilibrate. That's pretty interesting, isn't it? And as you come closer to the sample, what happens is, this is your tip sample gap, but at a certain point you reach a point where if you move the Z a little closer, you move the gap at which you are, tip sample gap, suddenly changes from being here to being somewhere there. You see that? Let me go back up. You're out here. As you coming closer is simply moving the origin of this green curve further to the left. So as I come a little closer, suddenly the tip sample gap from being here jumps to being here because that's the only possible intersection of these 2 curves. Okay? So the interesting point that we have seen already is that when you come close to the sample and move away from it, you can very easily get situations where there are regions in D that you don't access because there's a sudden snap-in phenomenon that happens. So you move the base of the cantilever close to the sample, the spring constant is equilibrating the attractive interaction forces, but at some point as you come very close, remember the attractive van der Waals forces go as 1 over gap squared. So they increase rapidly as the gap decreases, whereas the restoring force of the cantilever is linear with respect to deflection. So as you come very close, comes a point where the attractive forces are so large that they simply suck the cantilever in, and the gap suddenly changes from a value here to something here, and the tip has snapped into the sample, even though the Z still remains at a decent value. All right? When you move away, so what happens when you come into the sample is this: when you move away from the sample, you follow a different path. You would, when you retract from the sample and change Z, the intersection point follows along here until point 4, and then as you suddenly move it over to the right, the only intersection point is all the way here, and so it suddenly jumps out, okay? So what it shows is that when you take a cantilever and try to measure F versus D by changing Z, something very fundamental happens. You cannot access all the possible tip sample gaps by simply changing the base of the cantilever, because when you come closer to the sample, at some point the interaction forces are so strong that the cantilever snaps in, and you cannot maintain a certain gap. It snaps in. When you pull away, it snaps out. So the whole range of D values that you cannot access when you do FZ curves. It's a very important point, okay? So let's try to understand this a little deeper. This is the same curve on the left, F versus Z, and F versus D. But what we're going to do is to take this graphical representation we had on the previous page and convert it into what you would observe in an AFM, which is going to be cantilever deflection versus Z pairs of motion. Okay, so when you're at location 1, the interaction force is slightly negative. It causes a deflection delta. So what I do is, on the graph on the right, I plot, at that Z value, I plot a delta, a negative delta, which is a slight downward deflection of the cantilever. As I move to location 2, I have a certain Z value. I take the same Z value here, but here, the orange dot, 2, is at the same deflection as what you would get here, okay? And then as you come in, suddenly the deflection suddenly decreases. And so that's what you see here. You go from 2 to 2 prime. As you come in, the deflection suddenly becomes more negative as the tip snaps into the sample. Okay? Even though Z hasn't changed. You've changed Z very little, but suddenly there's a sudden change in D. And it snaps in. And then once it snaps in, as you keep pressing down on the sample, the tip actually comes back up again, right? So the deflection becomes positive. So initially, as the cantilever comes, it snaps in and pulls down, but as you keep pressing the base of the cantilever, the tips bends up, causing a positive deflection, okay? And when you come out, you get the opposite effect. You reach a certain point where it pops out and comes out, okay? So this is what you observe in an AFM experiment when you do F versus Z. You see this hysteretic behavior. Now, I want to emphasize that you get this hysteretic behavior even though the interaction force shown in red is perfectly conservative. It is the interaction force F versus D only depends on D, right? There's no hysteresis in this particular example in the FD, but the FZ shows a hysteresis as you come in or move away from the sample, right? So to understand this a little better, let's do a few examples. So what I want to go through here is how to convert FD to FZ a little more. Okay, let's do a few examples. Let's take the example on the top left. This is FTS versus D. It's a pretty odd interaction force. It doesn't look like Leonard Jones does it, or DMT, right? What is this interaction force? This is what we call a hard wall interaction force. When D is any value, there are no interactions, and then at D equal to 0, bam, you hit an infinitely rigid wall, right? Because F versus D becomes infinitely steep. So this is like a wall, right? So tip approaches basically no interaction forces it hits an infinitely stiff substrate. So you agree, I hope with me, that the F versus D curve is going to be as shown, right? It's a wall pretty much. So the question to ask is, if that is the F versus D, what is the corresponding F versus Z you would get if you try to probe this interaction using an AFM? What you would get is actually shown below, F versus Z. Think about it. So what happens is, now you've got a cantilever coming close to the sample, it touches the sample, right? So before it touches the sample, the deflection is 0. But once it touches the sample and you keep pressing the base of the cantilever down, guess what's going to happen? The cantilever is going to bend as much as you move the Z down, because the sample isn't moving, it's infinitely rigid, right? So the amount it bends, the cantilever bends, is simply equal to the amount you move the Z further down. In other words, the slope that you see here in the F versus Z curve is simply going to be the cantilever stiffness. That's it. That's the slope that you see. Because the deflection is going to be the same as the Z that you move on an infinitely stiff substrate. So I really want you to think about the first example on the left, FD versus FTS, F versus Z, right? This is really, really stark. It tells you FD is a straight wall, but F versus Z is going to show a linear ramp. I hope this tells you that these two things are very different, okay? So if you get a FZ curve where you get a slope that's equal to the cantilever stiffness, it means that the sample is effectively infinitely hard, okay? Let's take a look at the example, the second column here. Here you have a more realistic F versus D graph, which you would get, let's say, if you indented on, or if you're interacting with a complicated soft material, okay? So at a certain value of D, the interaction force starts climbing up and so on. Well, what is F versus Z going to look like in this case? If you really think about it, the curve that we got on the leftmost column forms the limit, the dashed line shown here. The dashed lines shown here in the second column happens to be the FZ curve you would get for an infinitely rigid substrate. But when you don't have an infinitely rigid substrate, you actually get more indentation into the sample, and the curve deviates from that you would get for an infinitely stiff sample. Okay? Let's look at the case in the third column. So the case in the third column is an interaction force that does become very stiff, but it does so gently, right? And what would happen in this case is, when you do the F versus Z, you're going to find that it gradually ramps up to asymptote to the slope equal to the K cantilever curve, okay? So I hope you understand and try to think a little bit about these interactions. They're very important to understand force distance curves. Now, to complete this discussion, let me focus on the Leonard-Jones or DMT-like interaction that's shown in the rightmost column, right? In the rightmost column, you see a F versus D as shown, and hopefully I've already demonstrated to you that when you do a FD to FZ conversion of this graph, you're going to get snap-in and pull-out instabilities of the cantilever. So when you approach the sample, your FZ curve is going to look as shown in red. It bends down and then snaps down at a certain critical point, and then it moves up, whereas when you withdraw from it, it follows the green line and snaps out, okay? So this we have already done, that a perfectly conservative tip-sample interaction force, which is only a function of distance, but just because of the cantilever instabilities, you have a situation where in the FZ curves, you get a hysteretic behavior, and you cannot access a part of the range of the D in the FD curves. Let us take a look at this interaction force, and I really want to highlight this issue. It's a very, very important issue, and it's one of the main reasons why people move to dynamic AFM instead of FZ curves to understand forces on surfaces. On the left here is a F versus D curve, which is hysteretic. Now, in this case, it's the FD curve itself that's hysteretic. And this is, for example, in the JKR model. And this is what happens due to the necking of the atoms when you have very soft materials. The neck, just the contact, the process of coming close and moving away, the interaction forces themselves are intrinsically hysteretic, right? So tip sample gap decreases, you get a formation of a neck. You break the bonds, you break the neck, you follow green. If you go through the analysis shown in the previous slide, you will find that actually the FZ curve corresponding to this situation will have the same features as the FZ curve shown on the right. In other words, it snaps in and pulls out. So this brings up a very interesting effect, that whenever you get these cantilever instabilities and it snaps in and pulls out, I have already shown you two interaction forces, one that's continuous and conservative on the top right, and one in the bottom left, which is hysteretic. There are two different FD curves, which could potentially lead you to the same FZ curve. So this is actually deep stuff. What this means is that when you have instabilities in snap-in and pull-outs, you are actually unable in any way to decide if indeed the interaction force takes the shape shown on the top right, or it takes the shape on the top left. So there is some non-uniqueness involved. How do you decide which ones? And so how people decide in this case is they say, well, I don't think my sample is going to have tip sample hysteresis. It's going to be more like a smooth DMT model because I know what materials are interacting. But if you don't know what materials are interacting and you don't have that knowledge, you really can't make that out. Okay? The second extremely important point is that just because the FZ curve is hysteretic, you snap in and pull out, it does not mean that the tip sample interaction forces are hysteretic. They're not, right? You can get a situation as shown on the top right, where you have perfectly well-defined interaction forces, smooth, no hysteresis, but indeed the FZ curve is hysteretic. Okay? These are very two important things. So it's for this reason, number one reason that when you get snap in and pull out, there's a range of D values for which that you cannot access, that is forbidden to you because the cantilever is not stable, it snaps and pulls out. So you'll never get the interaction forces in that range of D values. And the second reason that it's hard to distinguish between intrinsic hysteresis in the tip sample interactions and the hysteresis that happens in the FZ. It's hard to distinguish between these two cases from FZ curves. So because of these two reasons, dynamic AFM came about, where you don't bring the cantilever so close that you get a snap in and pull off. You stay far away and you oscillate with stiff cantilevers so that there's no snap in and pull out. And using that, they try to back out the entire F versus D curve. And remember, the physics is really, and the material properties are really in the FD curve, not in the FZ curve, okay? So, let's again revisit a little bit. So far we've been talking of, well, in theory, if you know FD, how do you get FZ from it? Now in experiments you're getting FZ, and let's revisit how in experiments you would convert FZ to FD. As discussed before, a typical FZ curve or a deflection Z curve you're going to get in experiments is shown here. You approach along the red, you get a snap in. You pull out along the green, you get a pull off, right? And what you can do by the simple geometry that I told you, so what you measure is delta versus Z. Delta is the cantilever deflection versus Z. You convert delta into interaction force by using the cantilever spring constant K, and you convert the measured delta and Z to the tip sample gap D. Okay, so again, what you're basically doing is you're taking the data set delta comma Z, you're getting at different Z's, you're measuring different deltas. So in an AFM experiment, you collect sets that are delta comma Z sets, delta 1, Z1, delta 2, Z2, and for each set you convert it into an F versus D using these two relationships. And you do it, you're going to find that the F versus D is going to contain a region which is undefined, because you don't know what the interaction forces are in this gap, right? Because this is the forbidden region. You're snapping in, you're pulling out, so you can never get the cantilever to maintain a gap that lies between these two regions, okay? And in these two regions is where you don't know if indeed the interaction force itself is hysteretic, or in fact this inaccessible region is happening because of cantilever pulling out or pulling in into a conservative interaction potential, okay? Give you an example of it and we'll wrap up this class. And this is a real example. This is on a carbon fiber composite. So what you see is a cross section. This is about a 10 micron by 10 micron image. In the circular topography things you see in the atomic force microscopy image are carbon fiber. Each one is about 2 microns, or actually 3 microns in diameter. And the area in between is a polymer, is an epoxy. So this is the kind of carbon fiber you might get in aircraft applications. In fact, it's sort of connected to a project we have with Boeing. And one of the things you could see in this is what you measure on a polymer is going to be the deflection of the cantilever versus Z. And that shows when you move in, snaps into the sample, you indent into the sample, move away. But when you go through the process that I just showed you, you're able to convert it into a force versus D, right? And you see the shapes are very different. Force versus F versus D is where all the physics is. Now, in reality, you do get some points in the region which is forbidden for some reason, just because, you know, the AFM is acquiring data at all points, and you get some transient areas here. So this area between here is typically the inaccessible area, but this is how you get FD versus FZ, okay? And when you convert to FD, the norm is to take the minimum value in the force here and assign D equal to 0 here. In this particular graph, it's D is minus 1 nanometer, but usually what you would do is once you convert to FD, you would take the minimum value and call it D equal to 0, all right? So that's how you convert FZ to FD, and with that, I'd like to conclude today's lecture. And in the next class, we're going to talk about some practical aspects of force distance curves. Thank you.